All right. So we have seen very important and integral components of the petroleum system and the processes. Out of those, the first process was the petroleum generation. So we have seen how petroleum gets generated, how kerosene is formed, what are the various types of conditions under which petroleum gets generated. So after the petroleum generation, then and this petroleum generation, it occurs in a source rock. And we all are aware what are the characteristics of a rock to be classified as a source rock. Now, once the petroleum gets generated, and we are also aware that the most common type of source rock, they are shales because of their non-permeability, impermeability. So it is also not easy to extract the petroleum directly from these shales by the artificial methods. So we need to have this generated petroleum to go to a reservoir rock. Okay, so from the source rock, it has to go to a reservoir rock. So we have seen what are the various types of reservoir rocks, what are their characteristic properties and all. And the process of the movement of petroleum from source rock to reservoir rock, it is called as petroleum migration. Very important process, because unless and until petroleum migrates, when I say petroleum, don't just focus yourself on the petrol and diesel or the crude oil. No, I am talking, when I say petroleum, I'm talking about gas as well. So here I am using petroleum as a common terminology for hydrocarbons. So the petroleum migration is a very important process, and it decides whether the companies which are looking for the oil or the gas, will they find it or not in a certain area which they are looking at. So the petroleum migration, as the name suggests, it is basically movement of hydrocarbon from source rock to reservoir rock. And you have also seen that how the reservoir rock needs to be augmented with trap and seals, so that once the petroleum reaches the reservoir rock, then it should not again then migrate away from the place of its accumulation. So with that note, let us start this topic, petroleum migration. Now, time and again, as I have been telling you all, that the petroleum migration, it is of two types. It is of two types. First one is the primary migration, and then of course the second one, you can guess the name, is the secondary migration. So how do we define primary migration? In general sense, the primary migration, it is the movement of petroleum from source rock to reservoir rock. Source rock to reservoir rock. While the secondary migration, it is the subsequent movement of oil and gas within the permeable carrier beds and reservoirs. So it is within the permeable beds and reservoir rocks. So for example, let me just draw a schematic diagram for you. Let us say that this is a bed which is the source rock, and this bed is overlain by another bed which is a carrier bed or it is a permeable bed. So let us say that the brown colored one, it is the source rock, or we can call it, we can name it as shale. Source rock. And let us imagine that the source rock is a shale bed, while this is a carrier bed. When I say carrier bed, it means it is a permeable bed. So let us consider it to be a sandstone. We know that sandstone is porous and permeable. So due to the processes that lead to the expulsion of hydrocarbon, this moves from the, okay, just a second, guys. So the movement of this oil vertically upwards to movement of oil to the carrier bed. Okay, so in this case we can see that there is a vertical movement from the source rock to the carrier bed, to the permeable beds. And this permeable bed, once it starts accumulating the oil or the hydrocarbon, then it becomes the reservoir rock. So the carrier bed only forms the reservoir rock. So what has happened? There has been a vertical movement from the source rock to the carrier beds or the reservoir rock. This is called as primary migration. End of story. That from the source rock, if this hydrocarbon, all these, this yellow colored, this is the hydrocarbon. So the source rock, which contains the hydrocarbons, once it expels the oil or the hydrocarbon to the overlying permeable bed, it is called as primary migration. Now, once the oil or the hydrocarbon enters this bed, now let us zoom it and make it here like this. Okay, so this is a folded sandstone or a let us say carrier bed or a reservoir rock, and this hydrocarbon, once it has entered here, now it can migrate laterally like this. So it can come here, it can come here, because all these pores are interconnected. Okay, they are, but this is a permeable bed. So in this case you are seeing that there is a lateral migration. So in the first case it was the vertical movement, and here now it is the lateral movement. This lateral movement is termed as secondary migration. So in the first case, the primary migration, it is from source rock to the reservoir rock and or the carrier bed, and the secondary migration is the lateral movement. So now comes the importance of traps, that through the secondary migration, now let us say that this hydrocarbon has reached the hinge of this anticline, which has the highest pressure. So it accumulates over there and this becomes a trap. Okay, so whenever we study the petroleum system, we cannot simply say that right now I am talking about source rock, then I will talk about the reservoir rock, then seal. No, we cannot talk about them in one by one. They are a complete system, and for the from the generation of petroleum to the accumulation of petroleum or hydrocarbon, you need to have all these systems in place together. Therefore, the concept of petroleum migration becomes important. Now, let us say that this trap over here is not very effective, it is not able to seal it, and then again this oil may migrate laterally in this direction. And a company which is drilling in this location say that this is the well, they are drilling in this location, but then the oil might have migrated to some other location due to secondary migration, so they will not get any useful or economic reserves of petroleum. So I guess this makes the things clear to you for the basic definition, that petroleum migration, which is of two types. The primary migration is a vertical migration from the underlying source rock to the overlying reservoir rock or the carrier bed, and secondary migration is, it is a lateral migration within the permeable bed or the reservoir rock. Now, what are the features or the factors that cause this primary and secondary migration? We'll see a little later. But whenever we talk about the petroleum migration, there are certain questions, a number of questions which arise. And what are the basic questions? The basic questions that arise in concern with the primary migration. So right now we are talking about the primary migration. So the first thing is the time. When did primary migration occur? Okay, so uh, was it after the maturation of petroleum, or was it before the maturation of petroleum? Okay, so what was the time once the migration occurred? Second is that what was the physical environment of the source bed during migration? Okay, the physical environment of source bed during that moment or during the migration. Okay, so when we talk about the physical environment, means we are talking about the temperature at that moment, we are talking about the pressure at that moment, we are talking about the porosity, and we are talking about the permeability. You may ask, sir, you are saying that the shales are the most common type of source rock, so why do you talk about permeability in them? That will come to see a little later, that how this permeability may develop in the shaly or the clayey source rocks. Then the third one, the third basic question that arises is that what was the chemical composition of the source rock at that moment? Was it a limestone, or was it a clay mineral? What was the clay mineralogy? What was the water content in it? Like that. So, chemical composition of source bed at the moment of migration. So, the chemical composition, it involves the clay mineralogy. If it is a shale, then sorry, clay mineralogy, then the water content, like that. All these are very important things. And the fourth basic question is, what was the nature of hydrocarbon? Was it petroleum, or means what was it, oil, or was it gas? Okay, so these are the four very important questions. The timing of migration, that was it along with the burial, was it after the compaction of the rock, or was it after the maturation, or was it before maturation? Then what was the physical environment of source bed during the migration? Means what was the temperature, what was the pressure, the porosity and permeability, and chemical composition of the source bed at the moment of migration. That is clay mineralogy, water content, and what was the nature of hydrocarbon, because oil and gas, that are two different carbons with different specific that means their densities are different, so specific gravities are different, so they will behave differently once the migration is going on. Okay, all right. So we are all aware that oil and gas, they are trapped in porous and permeable reservoirs, while the source rock, they are impermeable bed. This is the basic premise that we were talking about, that the source rocks, they are basically impermeable beds. Impermeable beds, while the reservoir rocks, they are porous and permeable beds. So how did the migration occur then? Because for migration you need to have some sort of mechanism in which this fluid goes out from the source rock to the reservoir rock. So earlier it was thought that oil and gas are squeezed out from the source clay during the early burial before compaction destroyed permeability. So let us say that you are looking at the clay particles which are loose, they are still not compacted, so the loose sediments, they have a lot of porosity in them, and within, so these are the loose clay, they have been buried. Okay, this is the loose clay which is buried, and this loose clay, it consists of let us say it consists of hydrocarbons. Okay, I'll make it with different color, it's not visible. So let us say these are the red color one, it is hydrocarbon. So earlier people used to think that once these were deposited during the early burial and compaction was not happening, they got expelled. But later on, people, you know, they realized this fact that even though compaction compaction destroys compaction destroys permeability. Remember that. We'll see in a bit how compaction destroys permeability. But if the hydrocarbons are expelled during the early burial, then the temperature required to generate hydrocarbon will not be reached. Okay, so this earlier idea that oil and gas are squeezed out from source clay during the early burial, it is not true, because the temperature required to generate hydrocarbon is not reached until compaction has greatly reduced permeability and water saturation. So understand this, that this compaction process is very very important. Unless unless compaction reduces unless compaction, it reduces the permeability and water saturation of those sediments, and water saturation, temperature for hydrocarbon generation itself, hydrocarbon generation is not achieved. Understand this fact, that what the compaction of the sediments is very important. Unless and until the compaction is there, it will never get generate that temperature at which the hydrocarbon is formed. Okay, so later on several studies were conducted. So this idea that the hydrocarbons, they are squeezed from the source clay during early burial is not correct. Now several studies have been conducted on the water expulsion by compaction. So studies have shown that most water expulsion by compaction, it occurs in the upper 2 kilometer of burial. So you should remember this, that water expulsion, water expulsion by compaction. Water expulsion by compaction, it occurs in upper 2 kilometer of burial. Upper 2 kilometer of burial. So now if we consider the average geothermal gradient to be 25 degrees Celsius per kilometer, then oil generation begins at the depth at which most of the compactional pore water has been expelled. So if let us say that the geothermal gradient is around 25 degrees Celsius per kilometer, and we know that the two after 2 kilometer only up to the 2 kilometer the water expulsion by compaction occurs. So at 2 kilometer depth the temperature shall be 50 degrees Celsius. So you all are aware about the oil window, that the temperature of oil window ranges from 50 degrees Celsius to 120 degrees Celsius. So we can see that the generation of petroleum will start when the water expulsion has happened to the maximum. So this first theory that the source sediments they expel out oil by squeezing before they get compacted is wrong, because the temperature of generation of petroleum it generates only when the water expulsion by compaction occurs, which is 50 degree Celsius at least. So this is very important thing, that the temperature for generation of petroleum is achieved only after the water expulsion by compaction has happened. That is water loss of water saturation. Now, these two are unrelated, but we can relate it by the geothermal gradient and the depth of the compaction. So, it has been seen that there are two types of water in the clays. There are two types of water in clay. One is called as the normal pore water. Normal pore water. So you know that if these are the clay particles which are loose, so they may have within these pores they may have water molecules like this. So this is water in the pores, and these are the clay particles. Second one, it is called as the structured water, okay, which is there in the lattice of the clay minerals. So one is the normal pore water, and second one is the structured water. This is structured water. It is bonded to the layers of the clay, especially the Montmorillonite. So, what is structured water? It is bonded to the layers of clay, especially the clay like Mont Morillonite. I am sure you have read about the types of clay minerals. So when I say layers of clays, because this is a phyllosilicate. Phyllosilicates, they have layers of the silicate structure. So let us just draw a type of structured water. It's a schematic diagram. So this is the silica tetrahedra in the layers like that. And then the water molecules, let us draw them this way. So how they are bonded to it? Like this. So you can see that the water molecules, they are bonded to the layers of the clay. So this is the structured water, while this is the clay. Okay, so we have two types of waters in the clay, the structured water and the normal pore water. So what happens is that the common type of clay minerals, they are elite, kaolinite, montmorillonite, okay, chlorite. So clays like elite or kaolinite, once they are buried, they they suffer a single phase of water emission because their compaction occurs in the first 2 kilometers of burial. So remember this, that elite and kaolinite, these are such clays which are compacted very early. They are compacted at relatively shallower depths, while the montmorillonite clay, it gets compacted after 2 kilometers of burial. So in case of, I'll come to this diagram a little late. Just I just wanted to write this, that clays like elite and kaolinite, they suffer from single phase of water expulsion. Single phase of water expulsion. Why does that happen? That happens because their compaction, their compaction occurs in the first 2 kilometers of burial. While in case of montmorillonite clay, in case of montmorillonite clay, it suffers two phases of water expulsion. Two phases of water expulsion. It is early phase, in which the normal pore water is expelled, while the late phase or the second phase, in this the structured water gets expelled. Okay, here structured water expulsion, structured water expulsion due to collapse of, or due to the breaking down of the lattice. So montmorillonite lattice, it breaks down and changes to elite. Okay, so it is during this late phase that this structured water, it gets expelled. So it has been seen that this Montmorillon. So look at this diagram now. All these, this is the clay layer. You can see here that the blocky things shown here, they are the clay. Within these lines, simple lines, they are the water which is contained in them. So this is water. Yeah, this one, this is water. So at a depth from 1.5 to 2 kilometers, which is written as about 3000 to 6000 feet. So this is a diagram from R.C. Shelley's book. Here, before the diagenesis, you can see that the clay particles, say this clay particle number 1, number 2, number 3, number 4, they are quite widespread. There is a lot of gap in between them, and they contain this normal pore water. Okay, but as this beyond the 2 kilometers, so 2 kilometer to around 3 kilometers, so what is happening over here? Here the diagenesis is going on and the montmorillonite is changing to elite. Here you can see that the during this breakage of lattice, during the breakage of lattice, you can see that this structured water here is now behaving as the free pore water over here, because due to you can see here all this water which was between the clay particles has now been lost. All these are compacted, their lattice has broken. See, this is the clay. Earlier, this clay was montmorillonite. Now it has changed to illite. So you can see that all the water in between these two clay particles, it is now lost because it was the structured water which is now behaving as the free pore water. And then, so what is happening over here, that after diagenesis and compaction beyond 3 kilometers, so it is beyond 3 kilometer, be more than 3 kilometer, you can see that a lot of compaction has occurred, and you can see how much volume is lost. Okay, earlier there was also all this water is expelled, all this water gets expelled, and due to expulsion of this water, all these clay particles, they are coming closer to each other, and see how much volume has lost. To attain this, there should be a continuous overburden pressure, so that the temperature generates to, or the temperature rises to the optimum level to generate the hydrocarbon. So it was shown by people that along with that hydrocarbon, along with that structured water, hydrocarbon may also be attached to the clay lattice. So I'll just draw a diagram for you, that along with the structured water that you saw here in this diagram, you can see that water is attached to the clay lattice. People have shown that hydrocarbon may also be attached. How? I'll just draw for you. Now I am drawing the clay lattice. So here they may be attached like this to the clay lattice, and this is the general formula for the, this is the hydrocarbon molecule. So like the structured water, this hydrocarbon molecule is also attached to the clay lattice. So it is quite possible that once the compaction occurs, so you saw here that during the compaction, this structured water was being expelled. So is it not obvious that during the compaction or during the dehydration, because this is the loss of water is called as dehydration, so during the dehydration of the clays, it is also quite possible that this hydrocarbon may also get expelled. Okay, so this is one of the ways by which the hydrocarbon may get expelled from the surface of the clay mineral. So this is the clay lattice. This is the structured water. And you can now understand that how the compaction of these clays may lead to the expulsion of hydrocarbons from the clay surface. So several geologists have suggested that the fluid migration from the clay, it is done through the development of microfractures. I'll show you a diagram of microfracture. So people have said that microfractures in the clays, they may develop by the increasing overburden pressure, and this microfractures, they significantly increase the permeability in the clay. So the microfractures in clay increase permeability permeability. And what happens is that, so as the fluids they escape through these microfractures, then they again close. So this is a microfracture which is seen in the clays, and you can see that through these microfractures the fluids they may migrate. Fluid migration through microfractures. Now, once the fluids they migrate, the pore pressure reduces, and then this reduction of pore pressure again closes the microfracture. So we have seen that the late expulsion of water, it plays a very important role in petroleum migration. Petroleum migration. This is what you should understand. So I hope till now you have understood the concept of compaction, burial, the expulsion of primary pore water and the or normal pore water and the structured water. Now, what are the theories for the primary migration of hydrocarbons? Because of both the kinds of migrations, primary migration is of optimum importance because it is only this where all the complexities are there. So theories for the primary migration of hydrocarbon. So the first theory says it is that expulsion of hydrocarbon, expulsion as proto-petroleum. Proto-petroleum. What does this mean? Now, one of the major problems in understanding hydrocarbon migration is that they are very, very less soluble in water. You all are aware that oil is never soluble in water. So it has been a, a major problem in understanding that if they are not soluble in water, how does the water expulsion aid in the expulsion of hydrocarbons? So the proto-petroleum theory it suggests that the immigration of petroleum or the hydrocarbons, not petroleum, hydrocarbons, it occurs when the hydrocarbons are in the form of ketones, acid, ester, which are soluble in water. So what does this theory say? The proto-petroleum theory says that hydrocarbon migration occurs when they are in form of ketones. These are all organic compounds. I'm sure you must have read in chemistry in your lower classes. Acids, organic acids, esters. And why they are talking about this these organic compounds, ketones, acid, esters? Because they are all soluble in water. So we all are aware that ketone, acid, ester, all these are the functional groups attached to a chain of carbon atoms. So let us say if we are talking about ketone, so it is a CO group, or acid, it is a COO group, like that. So this all these organic compounds which are soluble in water, they are in a transitional phase. So this phase this transitional phase is known as proto-petroleum. But you can now guess that this theory is not very correct. It is having a lot of problems, so many people have now discarded this theory and they don't accept, which is obviously very logical. Okay, now second theory says that the hydrocarbons they get expelled in aqueous solution. Okay, expulsion of hydrocarbon in aqueous solution. So here the idea is that Hydrocarbons may be insoluble in water at lower temperature and pressure, means at the Earth's surface, but quite possibly at very high temperatures in the subsurface, it might be soluble and get migrated as solution in aqueous media. So people have thought about several of these possible ways. So what it says, that hydrocarbons, they are insoluble in water at low temperatures on surface of the earth, while hydrocarbons may be soluble at high temperatures in subsurface. Okay, then once it is soluble, then it may migrate as aqueous media. So in that, so in this second theory, there was some subparts, that one theory was that it is a hot oil theory, second is the missile theory. Okay, so this second theory, it has two subparts: hot oil theory, and the second one is the missile theory. We'll see what they are. So the hot oil theory, what does it suggest? Hot oil theory, in this it was shown that several crude oils, they are soluble at temperature above 150 degrees Celsius, up to the order of 10 to 20 ppm. And yes, of course, this data is not very appropriate. And it was also shown that HC, hydrocarbon solubility, it increases with decreasing carbon numbers for both normal alkanes and aromatic series. So this is what you should know, that hydrocarbon solubility, it increases. Hydrocarbon solubility increases with decreasing carbon numbers, and this happens for both in case of normal alkanes and aromatics series which are unsaturated. So if you see this diagram over here, this is the carbon number and this is solubility milligram per liter. So as the carbon number is increasing, you can see from 0 to 36, you can see here how the uh, aromatics, normal alkanes at different temperatures behave. So if the uh, carbon number over here, it is lesser, the solubility is quite high. Okay, solubility of these hydrocarbons is very, very high, while the solubility decreases as the carbon number increases. So it is seen here by just this data that the solubilities are very high for paraffin gases. So paraffin gases. Now, when I say paraffin gases, they have carbons from 1 to carbon number 5. So they have maximum of 5 carbons. So paraffin gases, they have higher solubility, which is very evident from this diagram. So what happens? The gaseous hydrocarbons may immigrate by this mechanism from the source rock bed dissolved in the pore water, and X solution may occur once it reaches the lower pressure of the carrier bed. So what happens? Let us see that if this is the source rock and overlying this, it is the reservoir rock. Now these paraffin gases, so the gaseous hydrocarbons, if they are this, let us say these are the gaseous hydrocarbons, they may get dissolved in the pore water, and along with the pore water they may migrate to the reservoir rock or the carrier bed. Now, in the source rock, they were at high pressure. That is why they were dissolved in the water. But as the pressure reduces, so as they come in the permeable beds, their pressure, it drops. Pressure drops, and as the pressure drops, so if this is a water molecule which consists this gases, so the gases, they are exsolved at lower pressure. This is how the gas, it comes out of the pore water and then it enters the reservoir bed. Now, it is seen that of the typical crude oil, very little amount, it is composed of moderately soluble alkanes, while the the large component is, it is consisting of heavy aromatics and resins. So these are the ones which are consisting of heavy aromatics and resins. They are virtually insoluble in water. So this hot oil theory, it does not hold good for the majority of the crude oils. For the gases, we can logically see that it is okay, but for a crude oil, this theory does not hold good. Hold good because of the composition. Remember, at the very beginning of this lecture, I told you that the basic questions about the migration of petroleum or the hydrocarbon, where it is seen what type of hydrocarbon is getting migrated. Is it the gases or is it the crude oil? So if we are talking about the crude oil, we just saw that the uh, composition of this crude oil, it is very complex, and only 25% of it consists of moderately soluble alkanes. Remaining consists of heavy resins and other organic compounds which are virtually insoluble in the water. So the next theory that comes in place, it is the missile theory. It says that the micelles, they enhance the solubility of hydrocarbons. Okay. So water micelles, they basically are the colloidal organic acid soaps whose molecules have, they are bipolar. They have a hydrophobic end and hydrophilic end. So if you go back to your chemistry books of lower classes, you will know how the micelles are formed. But in case of hydrocarbons, they increase the solubility. So their presence may enhance solubility of hydrocarbon in water by acting a link between the OH radical on their hydrophilic end. So what happens is that these micelles, they kind of increase the solubility of the hydrocarbon in the water, and then they may help to uh, you know they may help in the migration of this hydrocarbon. But this is also not sufficient enough to explain the primary migration of the hydrocarbons. So the missile theory, or this missile theory and the hot oil theory, they basically are part of expulsion in aqueous solution. But this is again not a very promising theory for the process of migration. The third theory is the expulsion of oil in gaseous solution. No. People have done several studies, and now it is considered that directly or indirectly, carbon dioxide has significant effect on hydrocarbon migration. So CO2, it has a significant effect on hydrocarbon migration. So what happens over here, that if CO2 combines with calcium ions, it may precipitate calcitic cement. And once you all are aware, you have read the sedimentology, you know that once these cement is precipitated, it reduces pore volume and increases pore pressure. So if we have CO2 plus Ca2 plus, I'm not balancing the equation, you may have CaCO3 as cement. And this cement, what it does, it reduces pore volume, which is very, very common. Pore volume. Say, for example, if this is a pore, and in this pore, there is the formation of the cement, what it will do, it will definitely reduce the pore volume. So now the pore which was earlier quite big has been reduced to a smaller pore. So basically now this is the effective pore volume, which in previous case was very big. So this reduced pore volume, but at the same time it increases pore pressure. So if you have a water pipe in your garden and you want to increase the pressure of the water, what do? You close the mouth of the pipe and reduce it. So that the mouth size it reduces while the pressure of the water increases. So what happens? The presence of carbon dioxide gas in solution, it also lowers the viscosity of oil. So this pore pressure, always you should know that there is a certain limit to which the pressure may hold. Otherwise, if the pressure is going beyond the limit of that certain pore or the rock of that lithology, it will burst out. Okay, so the increase in the pore pressure, it is very important process for the expulsion of the hydrocarbon. Now, CO2 in the solution, it also lowers the viscosity of the oil. Viscosity, you know that if it is more viscous, it will not flow freely. If it is less viscous, it will flow freely. So uh, the carbon dioxide in the solution, it lowers the viscosity of oil and increases the mobility. As I was just saying, that it increases the movement. And the presence of carbon dioxide also, it leads to the precipitation of the heavy ends of oil. The heavier, like asphalt, grease, all these, they get precipitated, and the residual oil, it becomes lighter in nature. Understand this thing, that CO2, it helps in, or it causes precipitation of heavy ends of oil. Heavy ends of oil means the asphalt, graphite, grease, all these, they are precipitated out and makes the residual oil, means in which we are interested, residual oil makes residual oil lighter. And once this becomes lighter, it increases the gas to oil ratio, because the semi-solid part has now been precipitated out. So these gases, they play a direct role in oil migration. This is very important. So these gases, they play a direct role in oil migration. And hydrocarbon gases in deep wells, they are known to carry the oil in the gaseous solution. So hydrocarbon gases in deep wells, they carry oil in gaseous solution. So see, what is the, how important is carbon dioxide if it is present in the solution in the pores. So what it does, it reduces the if it reacts with calcium ion, it reduces the pore volume, increases the pore pressure. Then it also lowers the viscosity of the oil. How does it lower the viscosity of oil? It precipitates out the semi-solid part, which is the heavy part of oil, and the residual oil becomes lighter, increases the gas to oil ratio, and these gases, they bring up the oil uh, in the from the deep wells. So as these gases, they bring up, they carry up the oil, and the pressure and temperature drop, oil separates from the gases. Okay, so oil condenses out once the pressure and temperature drop, as the hydrocarbon gases, they are brought to the surface. So I hope you understood these theories of petroleum migration.